definition I have here, you don't have to write down, but you will notice that, and you can write it down if you want to, but number 9 says state the superposition principle and analyze the harmonic wavelengths for standing waves on a string. The superposition principle just means that we can combine waves. We can add waves together when they are reflecting and then hitting one another or something like that. I'm not going to ask you to write that down in that form though. So I'm not going to ask you to just tell me that definition. You need to understand the principle. That what it tells me is that we can combine waves in a manner like this here. But the definition itself, it's there, you can read it in your book, but I'm not going to have you define that word for word. What it says is that if I have two pulses, something like this, and it may be more complicated than two pulses, but if two wave pulses are coming in like this, and they collide, then they're going to combine and constructively interfere with each other there to give you one big peak right here. Then they both move off in their original directions here and move off from right to left here with this one, with that wave there, and then this one here, keep going to the right like that. And then over here we have destructive interference. When these two waves come in, they collide, and then right here in the middle, they then go down to nothing when they cross each other, and then keep moving off in their original directions. The interference of our waves is what's going to produce standing waves. So you're not going to see a clean standing wave here. But if I hold this here, and I'm oscillating like this, you can see this pulse. It comes back to my hand, right? Now if I keep doing this, then I just see a wave. But you'll get a couple points here where when I do that, you get an actual pattern there. And you might have seen it just briefly where it actually is going to do this, where there's just these nice little pieces like this oscillating back and forth, where it wasn't completely random, right? Where I could do this, and it's all weird, right? It's not doing anything, but at the right frequency, you can see how it starts shaking back and forth this way. And I'll show you more of that, but I'm near a standing wave pattern there. And we can get all these different, these are what we call standing waves. And the standing waves are produced from the interference of these waves on each other. This was all just me. I sent one in, but then it's coming back. Okay, and then when I was doing this, if it interferes the right way, and I was actually almost near the second, what we call the second one there. See how it's just going back and they're kind of getting bigger? And at that one time, it's almost like those two peaks and valleys are going back and forth like this instead of just a bunch of little ones. That's because they're interfering like this here constructively at those points. But it's only when I oscillate it at the correct frequency, or the correct frequency for where I was at here with this slinky. That's how we produce a standing wave. Yeah?
Did you ever see the Mythbusters where they take a little metronome device and put it on the bridge, and it says it's the right frequency, and it ends up moving this massive bridge, this little 10-pound weight?
I haven't seen that, but that's why bridges fall, and you've seen that
Yeah.
Tacoma Bridge fall in Washington.
Yeah.
Because when the wind was blowing at the right frequency, then you've created a standing wave there, and then you've created interference like this, which isn't good. You can have a helicopter rotor turning at the wrong frequency and make the whole helicopter shake violently. Because if it's going to vibrate or rotate at a bad frequency, which is one of the resonant frequencies of that device, whatever it is, the bridge, the helicopter, you'll have plenty of videos for things like that if you want to see things, bridges or poorly designed helicopters where constructive interference or these standing waves can be a bad thing. And things like a tube for a musical instrument, that can be a very good thing with sound because you're producing these nice clean notes, what we call these harmonics. Okay? We're going to talk more about that later on. But that's what one of those patterns looked like when I was saying I was doing that with the spring here. I had just one spring here, right? I was oscillating back and forth. And I get to a point where they interfere, and I get this nice clean pattern like that. Instead of a bunch of different things going back and forth. That's coming from the interference of these waves. That's from the superposition principle. That's what's creating these standing waves that we have. That's a wave on a string. A string tied to a wall there. You probably have a vibrating source right here. This could be something like a speaker or anything that you can tune and adjust to a different frequency. That's how you get those standing wave patterns. And let me just show you one more thing here.
Standing waves are a result of reflection.
Where's that speaker? Because I just asked you guys earlier on where was the speaker coming from, and I didn't see any speakers up here.
It's in there.
Okay. Because we were looking around earlier thinking that we didn't have speakers in here. So I was going to narrate this myself. Turn off those lights in the back, please, if somebody can. You might be able to see that better. I don't know how clear it'll be if I do this here, but
Standing get the third harmonic.
So those points that are kind of right there in the middle, you have these points going up and down, those points in the middle actually don't move at all. You could put something on there and you'd see that point not moving. It's kind of stationary. This is all one rope there, or one spring that I had right here. And you might have seen now that you're looking at it again, how I got to points where I was doing this here, and it was just something like that. Then I get to a point where I'm almost getting at one of those standing waves, where you can kind of, it feels more like it's going back and forth at you like this. You can create your waves with a slinky like this on your own. You could do it with a string like that. This would work better probably if I could give this a bigger amplitude, because when it's too close like that, it just looks like the wave are kind of traveling that way. And I could tell when I was hitting a standing wave, but you may not see it as clearly. If you stretch this out across the floor and made it bigger amplitude, you'd see it even more. And again, if you guys want to play, here it is. Speaking of playing around with physics, that question on the exam where I had the guy spinning around and dropping the bags, that was the homework question with the video. Did any of you try that on your own when you were at home?
Yes.
Good, at least somebody did. But I think if you did it on your own, and you spun around like that and you dropped them, there's no way you're missing that question. There's no way you don't answer that correctly because you've done it. And with things like these waves here, or with things like spinning around your chair, once you feel how the momentum's changing, or how you feel the different effects of moving your hands in and out, or dropping those bags, or maybe you have books or weights or something, I'm not saying you're going to learn it forever, but there's times like that where you can really get a much better feel for the waves, or maybe it's playing with the spring here or something, or slinky. But play with toys if you have them. It might make it fun. And that chair question on the exam I just put on there, thinking it would kind of be easy for those of you who remember that, but I think you'd remember it better if you actually did it. We're going to talk more about standing waves next week. I was just showing you that now while I had it up, and we were talking about the interference of these waves, and we actually saw it there with the slinky before I even really told you what it was. But we'll get into all the details of that next week. Okay, so you'll see here on this first page, I've given you graph paper with a couple of questions about simple harmonic oscillators here. And both of them, we're going to ask you to construct a graph of displacement versus time. On the exam, I will give you something in this same format. Well, I'll give you a piece of graph paper like this. I'll give you some information about something that's oscillating and ask you to draw a graph of that motion. Okay? So these are the ones we're going back now to that oscillatory motion of a spring going back and forth or up and down. And we're going to draw the mathematical wave that describes that motion. Whereas what we were just looking at was all these real physical waves, or the wave on the slinky or the string in that example that I showed you with that video. Okay. But you will have the same format though with graph paper like this on the exam, where at least one of them I'll ask you to draw a graph with a certain number of full periods in there. Okay. This is one of the things that's on your Mastering Physics in the course documents. I've given you a couple more in the same format like this just to give you some more practice of drawing these waves correctly. These are pretty straightforward, usually. You really just need to determine what the frequency or the period or the amplitude is to know how to draw that graph. Here you say you've got a mass 0.75 kilograms. We don't actually need that mass here in this case, but we have a mass oscillating on a spring, and it completes a cycle every half a second. What's the frequency of the oscillation, and we want to construct a displacement versus time graph from 0 to 1 second. Before we calculate the frequency, let's just draw the graph first. Okay. Now when you draw these graphs, they need to be drawn correctly, they need to be symmetric, and I'll just, with the graph paper here, you'll be able to do that. But you need to choose an axis or a scale for your axes here, and try to choose a scale so that your graph isn't all right in here. I mean, fill out the paper, or at least half the paper. Don't make a tiny little graph in there. Choose an appropriate scale to fit the paper that you're using, okay? To draw this graph, we need to know some things about the amplitude and the period. Here we don't know the amplitude. So we just choose a point here, A, and a point down here at minus A. If you don't know the amplitude, just call it A. Okay? That doesn't matter here to show me what this graph looks like. Label your axis down here, time in seconds. This can be displacement x here or y in meters. And if it says here that we complete a cycle every half a second, what does that tell me? What number is that representing? What would I call that? That is the period, because we complete a cycle every half a second. So capital T here is 0.5 seconds. Okay. It says here to construct a displacement versus time graph from 0 to 1 second. Okay. So I'm just going to put 1 second over here. Now when you're doing this on graph paper, before you actually mark these points, you need to decide on your scale. Okay. But on your graph though, I don't want, if I'm making a complete cycle in 1 second, then it would be a very poor choice if I chose each box to be 1 second. Right? I can't draw a full cycle. I could, but I don't want to draw a full cycle here in one little box. When you pick these graphs, remember, you know what they look like. They're going to look like this. You know exactly what these should look like. It's just about you choosing the appropriate scale and labeling your axes properly. Okay? When you draw these graphs, assuming it's simple harmonic motion, this is going to go on forever. You can start wherever you want. Physically, when we took that mass from here and we oscillated it, or pulled it out here and let it oscillate here, you might think, well, I'm going to start out here, or start in here. Doesn't matter where you start. When you draw these graphs, you can start anywhere. It's usually going to be easiest if you start at 0, because I think that's going to feel more natural for you. Physically, you probably start over here if you're going to pull it out and let it oscillate. So you might think, well, I'm really going to start up here. But this graph is the same all the way through, so you can start anywhere. It's like you're just starting your clock when I've come back to this point right here. Okay, but I think it's going to look better to you when you're drawing the graphs if you start here. Okay, either way, we need to show 2 full periods here because we have the period being half a second, so in our 1 second, we're going to have 2 full waves. Okay. Over here, 1 full period, if I start from here, is from here to what point? This point? The next point, right? This is 1 period from there to there. This can be divided up into how many parts, how many even parts? Well, I've got a piece up here and a piece down here that's symmetric, right? So that's kind of 2 halves there. You could also think about it in quarters like this. And these are the points where, when I'm using a graph like that, and you have a grid of graph paper, I want to mark the point here in the middle as a reference point, because I know I need to cross through that point. I also need to know that I need to go through the peak up here and the trough down here. But these are right at a quarter of the whole thing, right? This is a quarter of the wave, that's a half of the wave, 3/4, and the full 4/4 of the wave here. You guys see that? So if you're thinking about that your wave can be chopped up in these 4 parts right here, then you might think about choosing your scale or choosing your boxes so that you can mark these points at 1, 2, 3, and 4, and then 1, 2, 3, and 4 over here at 1 second. So you can divide it up evenly and draw it nice and symmetric about the axes here. So here, this would be from here to here, half a second there, where I have now 4 boxes in between every half a second. That's going to allow you to say, okay, that's the middle of the wave, that's the end of the wave there. This is the peak up here, this is the trough down there. And here's the points where I'm saying, you see the graph like this now? Those are my reference points that I really want for me to be able to draw this symmetrically. I want to see here, here, there, and then the points on here. Those are the points of reference that you probably need to draw the graph. So I think you all know what 2 full periods looks like. You could have said, I'm going to start like this, and I'm going to go up and down like this. But when you just draw that on a piece of graph paper, it's probably not going to be symmetric, or it may not be perfect. Okay? And so you might just sketch it and you feel, well, okay, this one's skinnier than this one over here. To get it to be nice and smooth and everything symmetric here, these are points that you should just label on your graph, because then it'd be very easy to say, okay, I know how to connect or make the curves that go through these points here. Okay. That makes sense here when I'm talking about the symmetry that we need to have for these graphs, that they all need to kind of go through these points down here with the amplitude. Otherwise, you could just draw that graph and you'd be crossing through all random points in your boxes down below on the t-axis, and it won't be clean. That's why I'm saying I look for those points, or I want to label those points and think about those points when I'm choosing the scale here for my horizontal and vertical axes. These don't have to be perfect, but I really shouldn't see this peak here being over here. And I shouldn't see this point here being higher than this point down here. They need to be symmetric, and again, it may not be perfect here. This one might be a little bit wider than that one. You don't know exactly, how curved this should be. What I don't want to see on your graphs are graphs like this. You can't show me V's, or don't show me big U's like this either. It should look basically like that there. Okay. And I see a lot of you erasing a little bit. It'll take you a couple times to practice these and make your graphs nice and smooth. But I do want you to be able to draw these and be able to read them and know how to find things like the period or frequency from a graph. Or take that information and be able to plot this graph. So we told you here, plot this graph for 1 second. Once we knew the period, we then knew how many full waves would be inside of this 1 second time interval here. And that's where I'm saying you have to know what these numbers represent, how to draw the graph. Okay. This isn't a ton of points, but this could be, if you need information about the period or frequency, this may be a 10-point question sometimes with the graph and a couple of numbers here to have you calculate something else. Once you do these a few times though, this shouldn't be very difficult. Okay. There are a couple more to practice on in your course documents area. You all have nice clean graphs now, hopefully? Okay. So what else I want to point out here though is that sometimes with these graphs, if I tell you to graph it for 2 full periods or for 1 full second, then don't go any further than this 1 second here. Sometimes people will graph and then go further on over here and then stop up there. If you don't have it exactly where it should end, or you have extra parts or not enough parts, that's not the correct graph for the time interval that I've asked for here. So just make sure it should be exactly for, in this case, 1 second, which is 2 full complete waves. How do we find the frequency? Or what does the frequency mean? Number of waves per second. How many waves or how many full cycles do I have here per second if I just look at my graph? Here's 1 second, I see 2 there. You could have calculated it from this also though, right? What's frequency in terms of period? 1 over period. We did that last unit. I don't think I wrote it down again today, but write that down so you have it somewhere if we didn't list it yet today. Well, we know these two things are just inversely related. You can see that from the graph, and you can read that from your graph, and you really don't need to show me the equation here if you just read it from your graph. This is an easy case where we're going to 1, so you can clearly see here there are 2 full cycles there, 2 full waves in that 1 second. But here we get 2 hertz for our frequency. I don't know if I asked you for that or not. Did I? Yeah. We could have found that before we saw the graph. I just waited to the graph because you can see it clearly here, I think. You should be able to draw these graphs. You should also be able to read and interpret the graphs. Okay, so let's look at number 2 now. And I'll give you a chance to draw this one on your own. You've got a particle here that's going to oscillate in simple harmonic motion with an amplitude of A. We want to know the total distance in terms of A that the particle travels in 3 periods. And I want you to construct a displacement versus time graph showing 3 periods. So go ahead and try that. Choose a convenient scale so that you can kind of fill this up in your paper here. Maybe like we were thinking about before, where you might want to divide it up into some even parts here so you can get that all marked on there. Draw your 3 full periods and then see if you can determine the total distance in terms of A that a particle travels in those 3 periods. But just start with that graph there. I'll give you a minute to draw those out.